Okay, right. Welcome everyone to the IIT Bombay Virtual Competitive Algebra Seminar. We are happy to have Kazuma Shimomoto for his second talk on perfectoid spaces. So Kazuma, I invite you to begin your seminar.
Okay, thank you so much. So I'm going to talk about the second part of the perfectoid spaces. So, so do you actually see my slides? Are you okay?
Yes, yes,
I
yes,
know you hear my voices.
yes.
Okay, thank you so much. So last time I was talking about some story of perfectoid spaces and plus some technical parts, but suddenly I just screwed up, and I just apologize to you if my talk was not so organized. Then I was thinking about how I reorganize my second slides, but I thought that I would just shrink the size of the slides, but then I decided to just contain more and more, because maybe I think it would be useful for people to just get information from my slides. So I will just skip, sometimes I will not just cover everything in the slides. Okay, so let me first the direct summand theorem. So it was called the direct summand conjecture. Now this is a theorem. It's a recent breakthrough done by Andre, and in the other cases, namely when the ring contains a field, then this was done previously by Hoxter. So let's just begin with the statement. The theorem goes as follows. It's somehow quite simple statement. And if you don't know much about the regular local ring, so you can think of something like polynomial algebra over Z localized at some prime ideal. So let R be a regular local ring, and then we take a map from R to S to be module finite extension. So namely, I'm assuming S is an integral extension over R such that S is finitely generated R module. And then also I assume S is a domain. Then R to S splits as an R homomorphism. So this is a statement. So if you want to understand Andre's proof of the direct summand conjecture, so the main actual tools, so what kind of ideas are used in his proof, or somehow which these actual tools you can take as a black box. So the ingredients are the following. The first one is almost parity theorem. The second one, Andre's lemma on almost faithfully flat perfectoid cover. So I'm not going to talk about the second one. So I'm going to talk about the first almost parity theorem. So my understanding is that assuming these results, so most part of Andre's proof of direct summand conjecture uses tools from the traditional commutative algebra. And also, as far as I know, more recent proof of the direct summand conjecture is getting shorter, and namely doesn't even need the almost parity theorem. But I don't think this was written in paper. I hope to see this was written in maybe some paper or book. Okay, so this is a direct summand theorem. So this is just rough information. And then again, I have somehow skipped from time to time. So let's just begin with somehow the almost parity theorem. So as far as I know, the almost parity theorem have different, several different proofs. The first one reduces to the case perfectoid fields plus in the Henselian approximation. And this proof heavily relies on the geometry of the perfectoid space. So namely, we really need some geometric argument to prove the algebraic statement. And also I'm give a precise statement of almost parity theorem later. And the second proof is done via more recent prismatic homology, which I don't quite understand. So this cohomology theory is somehow more like number theoretic in the context. So it has a somehow Frobenius operator, and the prismatic homology, I think, is just coming from the somehow arithmetic homology, so-called crystalline homology. But you don't have to worry about the crystalline homology. So here's just a punchline. So why is it better to think of prismatic homology? So here's a slogan. So for a proper smooth variety X over a perfect field of characteristic P, so crystalline homology of X is roughly the drum homology of a smooth lift of X to the bit vectors of K. So namely, X is a variety over K, and if you have a somehow deformation or lifting of variety to some smooth scheme over the bit vectors, then crystalline homology is just drum homology. But unfortunately, this is too naive because, first of all, we cannot expect have a find a lift X from the residue field to the bit vectors. But nonetheless, the drum homology, which is defined in characteristic 0, has a Frobenius action. So this is very important. And let me just only say just this slogan. I think you can just read other part of the slides in this page. So somehow, why cohomology is better than the rings or schemes? So somehow it is easier to deform cohomology from characteristic P to mixed characteristics than to deform rings or schemes. So usually we start with ring or schemes, then we have a Frobenius action, then we look at the Frobenius action on the local cohomology, for example. Then we define the Frobenius action, which comes from the ring. Somehow the prismatic homology ignores the underlying space. But then instead we have cohomology with Frobenius action. So I think maybe in the future we should study maybe prismatic homology if you are interested in maybe some problems in a mixed characteristic in local homology, because we have somehow something like Frobenius action. Okay, so anyway, so this is not so important today. So today I'm going to give more concrete information about almost ring theory plus perfectoid spaces. And I'm going to pick up one specific application to get familiar with perfectoid techniques. But however, you don't have to know many things beforehand. You only need one tool. That is Frobenius map. Okay, so let me give some definition. So let's start with some basic definition in almost ring theory. So fix just any ring A with an ideal I such that I squared is equal to I. Then we call such a pair a basic setup. Okay, so we just pick any ring and then any ideal satisfying I squared is equal to I. For example, I could be 0 or I could be a unit ideal. Then let's take M be a module. Then M is I almost 0 if I q's M. Next, let's take F from M to N, A homomorphism. Then F is I almost injective, respectively I almost surjective. If kernel F is almost 0, respectively image of F is, sorry, so this is not correct. This is co-kernel, sorry. So this should be co-kernel, is I almost 0. So I'm going to just make corrections later. And finally, F is an almost isomorphism if it is both I almost injective and I almost surjective. So by the way, if I is a finitely generated ideal, then I is generated by an idempotent. So the essential case is when I is not finitely generated. So for instance, most basic example is the following. So let's take the basic setup to be the pair, this one, which is ZP. Then again, you adjoin all P power roots of P. Then you get a very huge infinite integral extension. And the ideal is generated by all P power roots of P. In this case, this is a non-discrete valuation ring of rank 1. And if we take periodic completion, its periodic completion. Sorry, this should be its periodic completion is an example of a perfectoid evaluation ring. So by definition, perfectoid means complete. And moreover, if you remember, my talk in the last time, its tilt is given by the periodic completion of a polynomial algebra, and then adjoin all p power roots of t. So where t is just indeterminate over fp. So quite often, so we take this ideal to be ascending union of principal ideals. So these are just only basic examples. Okay, so to understand or to appreciate the idea of I almost zero modules, for example, let's take M to be the quotient. Namely, take this ring and modulo this ideal, which is a residue field, Fp. Then this is not zero, but this is almost zero. So this is a non-trivial example. I almost zero doesn't imply it's zero. And the second, in characteristic P, almost ring theory is easy to understand, and there are many tons of non-trivial examples. So we should start with characteristic P, then mixture characteristic. And many notions in classical ring theory carry over to the setting of almost rings and modules, such as I almost flat and I almost projective, I almost et al. And for instance, an A module is I almost flat if distortion is killed by I for any I greater than 0 and any A module n. So this almost something depends on the choice of I. So that's why I say I almost something. Okay, so here's, I think, one basic example, which maybe you will find some interesting, maybe useful in today's slides. Okay, so let's take R to be a characteristic P ring, and then we just recall the perfect closure, or maybe direct perfection of R. I think I used a different terminology, but I decided to use R infinity to be just ascending union of over rings of R by adjoining all P power roots of R. So it's just ascending union, and then take all just n, then we get very huge extension. So here's some very important basic results. I think it's just baby example, and I will explain the proof in detail. So statement is as follows. So let's take our complete Noetherian local FP domain. So this is characteristic P, and just choose a system of parameters x1 through xd of R. Then there's a basic setup such that R infinity is I almost Macaulay. So this means that if you look at this column ideal, modulo the ideal generated by x1 through xi, this is not, maybe not 0 or maybe 0, but at least it's killed by I. So by the way, so I have to make a choice of I. I don't say you can take arbitrary I. So in this case, how do I determine I? It's determined by the following. So since R is complete, so there is an element, non-zero element in C in R, such that localization is Macaulay, or even we can take C to be regular. So then we simply set I to be the ideal generated by all P power roots of C. So this is this satisfies basic setup. So notice that R infinity is a non-Noetherian Macaulay ring. So namely, sorry, so this is not a non-Noetherian almost Macaulay ring. Sorry, so this should be almost Macaulay ring. So here's a proof. So since R is complete, we can find a modular finite extension from the power series ring over K. So let's say this A to R. So then there is an integer M, so together with some element C. So this C is actually the same C as I mentioned above. Then such that there is an A modular map. It's just M copies of A to R. such that core-kernel is killed by C. So you can actually construct this as injection, and such that the core-kernel is killed by C. So then in this case, x1 through xd forms actually system parameters that consider the relation. So because the obstruction for a parameter to become a regular sequence is just because there are somehow non-trivial relations. So let's take some relation, which is this. So you take the sum of ak times xk, and then I choose index from k to 1 until I minus 1. Then if I look at the xi, so this really means xi times map of the ring R infinity modulo the ideal generated by x1 through xi minus 1. So this, if we rewrite this, it's just a relation. So if I look at the xi times map. So let's just throw these elements ak to R to get some other ring, which is R prime. So this R prime is, of course, subring of R sub infinity. So let's just replace this R by R prime without loss of generality, and then simply just take R prime to R. So in other words, R contains this AI. So now the next point is just iterate from this. So just iterate this, usual from this. Then we get from 1 that the following relations. We simply apply the Frobenius as many times as you want. So this relation holds. Okay. Just because we have this relation, this can be used to deduce this relation. Okay. So then it is quite obvious that the sequence is regular because it's just because A is regular. So it's M comp is A is just Cohen-Macaulay, which means this forms a regular sequence. So therefore, we have C times A to the P to the N. So in other words, so this relation somehow can be trivialized. Okay. So in other words, so this, let's say, okay, so this is a regular sequence. So this regularity shows that this C times A to the P to the N is contained in this intermediate ideal, which is further contained in this ideal. So that's why I use A. So because this is regular. Then taking the P to the nth roots, then we obtain the following relationship. So this, okay, so what does this mean? So this means that this A is somehow killed by C to the 1 over P to the nth root. So in other words, if I take pi n, it's just P to the nth root of C. So this element kills relation among the system parameters I started with. So this is just a baby example. So since R is Noetherian local domain, so this final step, so it is arithmetically complete and separated. Using this fact, so we can prove that R infinity is also arithmetically separated. So by the way, this R infinity is not arithmetically complete, but at least arithmetically separated. So suppose that we have this relation, pi n times R infinity is contained m times R infinity for all n. In particular, so this, of course, says pi sub n is contained in m times R infinity. So after raising P to the nth root, nth Frobenius power on both sides, so we simply get this. I think, sorry, so this should be, I think this is intersection, not let's say, I think this should be intersection, sorry. So because this is emadically separated. That means if we take a higher from its power, then this eventually goes to 0. So this should be intersection. However, we don't take C to be 0 element. So this is a contradiction. So in any case, this, if you, I will provide slides later. So if you want to get better understanding, so if you just learn this example, so you will get ideas how to apply this kind of method to mixed characteristics case. Okay. By the way, you might wonder so whether R infinity is big Cohen-Macaulay algebra. So for example, if you take R to be non-Cohen-Macaulay local domain that is F pure, then this map from R to its perfect closure must split. So therefore, if R infinity is Cohen-Macaulay, that means R must be Cohen-Macaulay. So we can construct example R that is non-Cohen-Macaulay but F pure. Then we provide example of R infinity that is not Cohen-Macaulay but almost Cohen-Macaulay. Okay. So we have tons of almost Cohen-Macaulay algebra, so using this theorem in characteristic P. So in some sense, almost ring theory is not empty theory. So this is my point. So there are there some questions?
No, I don't see any question. I had a question about the choice of the element C. C looks like a test element to me.
Yeah, yes. It's actually, I think it can be, there are actually maybe different possible choices. So it's something like test element, yes.
Yeah. Thank you.
Thank you so much. Okay, so after learning, somehow get kind of sense of what's going on characteristic P. So let's move on to the just harder part, which is mixed characteristic. So this is almost parity theorem. So the statement is as follows. So let's start with P torsion free integral perfectoid ring such that A contains all P power roots of P. Actually, we don't need this assumption, but let's just make simple. Okay. So then what's my assumption? So my assumption is that, so let's take a ring extension from A localized at P. So you invert P. So this is a prime number P. From this ring to some finite état extension, which is called just B prime. Let's take B to be integral closure of A in B prime. Then we have the following statements. So B is a perfectoid ring. So this is P complete, periodically complete ring such that if we mod out by P, then Frobin is surjective and the kernel is actually generated by P to be one over Pth roots. And so what is more important is the second statement. This extension is actually almost finite étal with respect to this idea. So now this is a precise statement of almost parity theorem. So why actually it's called parity? Actually, it's connected with the classical Zariski-Nagata parity theorem because it says somehow some equivalence of categories of some finite étal algebras over somehow over A localized at P, and the category of almost finite étal algebras over A. So it's actually the classical, counterpart. This is actually modern counterpart of the classical Zariski-Nagata theorem. But if I was looking at this statement for the first time when I was a graduate student, I was completely lost because I had no other information. So I was just only spend lots of time in order to understand why this is called parity theorem. But now everything is clear. But I guess it's not clearly written in any papers or the lecture notes. So I'm just writing lecture notes, which is still under construction. Then I make a list for references. So if you are interested, just learning more, so I can send the copy of my lecture notes. So just please send me a message. So you can find also my email address in the end of the talk. By the way, so the basic example is, of course, if you, what kind of A? So A is something like, this algebra, so which I saw last time. And this hat means just periodic completion, or you take some power series of ZP, then you adjoin, many variables, as many as variables as you want, and then adjoin p power roots of each variable. Oh, sorry. I think I forgot P. Also, I should adjoin P power roots of P. Sorry, so lots of just typos in my slides. So I have to adjoin P power roots of P on both sides. Otherwise, it doesn't make sense. So by the way, why do we have to take periodic completion? Actually, there's a version of purity theorem due to Davis and Kedolaya. So they don't take periodic completion. And also, let me tell you something about the proof of almost purity theorem. Actually, there's also the version of characteristic P, and you can find it, for example, Gaba-Ramero's almost ring theory or Barga-Bat's lecture notes. So in any case, you can formulate also almost purity theorem in positive characteristic, but this is quite easy. I mean, this proof uses only standard commutative algebra. But however, so this version is mixed characteristic. This is much harder. So this mixed characteristic version actually requires the almost purity theorem in positive characteristic. Actually, this is the first step. The second step, just reduce to the case is perfected evaluation ring. So this is quite essential. And even in this case, there seems to be 3 different proofs. The first one done by ramification theory due to Gaba and Ramero. So they have the first lecture notes. The title is almost ring theory. The second case is a reduction to the case A is absolutely integrally closed. So this is, I think, due to Schultz in his paper of perfected spaces. And recently, I and my student Ishiro gave a new proof using Falting's normalized lengths and Frobenius-Pullback formula. So I have no time. I don't have much time to explain what's the Falting's normalized lengths and the Frobenius-Pullback formula. But this is also pure commutative algebra. So if you are interested, we have a preprint on archive, so you can get access to the papers. Okay, the third step is, which I don't talk so much, so equivalence with the categories of étale algebras under completion and Henselizations. So this is somehow doesn't say anything, so I will skip it. And also topological isomorphism of perfected spaces under tilting. So this is quite a global geometric argument. Okay. So here I can suggest some research problem. So can one give a purely algebraic proof of the almost purity theorem? So in mixed characteristic. So as I said in the last page, characteristic P version is quite elementary. But however, mixed characteristic requires several different steps. And I still don't know how to prove it in purely commutative algebra technique. So here seems to be, it's somehow challenging to algebraists to try to find out purely algebraic proof, or maybe let's say standard commutative algebra proof. Okay, so here is also one thing I really want bring to people's attention when you study perfectoid geometry. So in my understanding, perfectoid geometry has many aspects. So one aspect is, of course, it's quite huge ring extension. You have to take p power roots of p. You have to take quite a huge extension. So it's really non-Noetherian object. But eventually, we want to understand something which is Noetherian. Then we have to take higher and higher extension in order to get the information to the original Noetherian ring. So this is somehow ascending to the top, then descending down. So another aspect of perfectoid geometry is just monoid. Okay, so let me just explain just a little bit what this is. So it is often useful to regard a commutative ring as a multiplicative monoid. So we have just addition and multiplication, but we completely forget about addition. We only think of multiplication. So here's just one example. So let's take K to be a perfect field of characteristic P. And let's take WK, the ring of Witt vectors. Then there's an injective multiplicative map, just called the Teichmüller map, which I denote by bracket. This is a map from K to WK, which is multiplicative, but not additive. So for example, if I take K to be a finite field, Fp, then this WK is just ZP. So this is a ring of periodic integers. Then we have a embedding of Fp to ZP. But however, this is characteristic P, this is a characteristic, or this is a mixer characteristic. So it's impossible to have a ring homomorphism from characteristic P to characteristic 0. So what is the image of this Teichmüller map? The image of the Teichmüller map is actually identified with this subset. So the point is, in perfectoid geometry, is to generalize this construction as follows. So let's fix a prime P, and let's assume A is just any periodically complete ring. So you can take a Noetherian ring or non-Noetherian ring, but I require only periodic completeness. So we consider the multiplicative map from A to itself, defined by x goes to x to the pth power. So this defines an inverse system, and we get the multiplicative monoid. So by the way, if A is already characteristic P, this is nothing other than just Frobenius map. But I don't assume A to be FP algebra. So if we form this inverse limit, we don't get commutative ring, but we get multiplicative monoid. And also there's a commutative diagram, which is this. So, sorry, this has to be A. So this top horizontal map is just a multiplicative map, but this lower is just Frobenius map. So using this commutative diagram, you can take inverse limit. So we get to the multiplicative map, which is this. So in this case, you can just go to left. So from A to A, so you can form in the inverse system by going to the left from the right. So next theorem is quite fundamental perfectoid geometry. So perfectoid, this actually says, so let's take just notation B as previously. Then this map as just multiplicative monoids is a bijection of, this is just a bijection of multiplicative monoids. So this map is exactly the same as this one. So actually, the construction is not so hard. So if you're familiar with monoids, it's just a hands-on calculation. So using this theorem, so we can define the multiplicative map, which is quite important, this sharp map from A flat to A. So this A flat is characteristic P ring, and this A is, let's say, when A is a P torsion free ring, this is a mixer characteristic ring. So let's define this map as a composite. Namely, you take inverse of this bijection, which is this, then take projection from the inverse limit into the first factor. So this composite is just written as sharp. So this map is extremely useful. As I said, this is not ring homomorphism. This is just multiplicative homomorphism. And actually, Kedolai calls it homotopy map because it can be used to the perfectoid spaces. So for example, if I apply this map, you can construct the homomorphism of this SPA. So I don't discuss what is SPA. These are just some perfectoid spaces, but I don't talk about it so much. So anyway, this homomorphism is induced by the monoid map, not by a ring map. So usually if you take, for example, if you start with a ring homomorphism from A to B, then you can define the corresponding map on affine schemes. Well, this SPA, this map is also similar to that situation, but the only difference is this doesn't come from any ring map. So here's also, I think, the reason why we should consider monoid construction. So second is if we periodically complete p-torsion-free ring A has the additional property that A mod P is perfect. So namely, Frobin is bijective. Then if we take the bit vectors applied to A mod P, then this is isomorphic to A. And in this case, the sharp map coincides with the type mirror map. So therefore, the map sharp is a generalization of part of the theory of bit vectors. Okay, so anyway, so this is also important. So I cannot say much more than that. So let's just move on to another topic. Okay, so in perfectoid geometry, we often deal with non-Noetherian rings. But can we actually discuss any non-Noetherian ring? So the answer is of course not. So we have to somehow pick out nice candidates of non-Noetherian rings to study perfectoid geometry. So let's just recall absolute integral closure. So let's take A to be an integral domain with field of fractions. And let's take K bar is algebraic closure. So we define absolute integral closure of A is defined to be integral closure of A in K bar. So we don't denote this extension ring by on A plus. So by the way, if A is not a field, A plus will not be Noetherian. So actually, here is a very well-known theorem. Any finitely generated ideal of Z plus, namely absolute integral closure of Z, is a principal. So I'm going to skip a proof because this is not quite important. So this is, I think, the first non-trivial case of the structure of Z plus. So it uses some algebraic number theory. Okay, so other than Z plus, so what do we know about R plus in general? So for example, so this is a theorem by Hochster, Hünecke, Rivesnik, and Kui. So let's take R to be Noetherian local domain characteristic P. So assume that R is a homomorphic image of Koeh-Macaulay ring. Then R plus is big Koeh-Macaulay algebra. Namely, any system of parameters of R is a regular sequence of R plus. And in the mixed characteristic case, so Barger-Batt proved the following quite remarkable result. So let R be an excellent local domain of a mixed characteristic. Then the periodic completion of R plus is a big Koeh-Macaulay algebra. So if we don't take periodic completion, this is still big Koeh-Macaulay algebra, but you have to start with regular system parameters such that the first one is P. So this is a big difference. Because usually big Koeh-Macaulay means some system of parameters regular sequence. But when we say every system parameter is regular sequence, we have to say balanced big Koeh-Macaulay algebra. So actually, Hochster Hünecke proved, so when R is excellent, then extended by Kui to the case that R is a homomorphic image of Koeh-Macaulay ring. So by Takeshi Kawasaki, it is known that an excellent local ring is a homomorphic image of a Cohen-Macaulay ring. So I think in characteristic P, this result done by Kui is the best result, I think, as far as I know. And also, in positive characteristic, we already saw tons of examples, almost Cohen-Macaulay algebra, that obtained, constructed as a perfect closure of R. And but uses again the prismatic homology, which I don't quite understand. So, but actually, his idea is inspired by the method, used by Hunek and Rivetsnik, because he also had to prove that R plus is almost Cohen-Macaulay. As far as I know, I just read some parts of his papers, so it sounds like we really need it. So now here comes a question. So I talked about almost Cohen-Macaulay algebra, but we need Cohen-Macaulay algebra, not almost. So why do we care about almost something, almost Cohen-Macaulay algebra? So here is the answer. So the answer is that, so once we can construct almost Cohen-Macaulay algebra, then there's a technique which Hochster is used in his construction of big Cohen-Macaulay algebra. So this is called the partial algebra modifications. So I think I forgot add reference Hochster's paper in the end of the talk. But there's a paper, Hochster's paper published in 2002 or 3 from Journal of Algebra. I think the title is Big Cohen-Macaulay Algebra Dimension 3 via Heitmann's theorem. So there actually he explains what's a partial algebra modification. So we can use this technique to construct a genuine big Cohen-Macaulay algebra. So if we can go straight forward to big Cohen-Macaulay algebra, so that's quite nice. But I think somehow we have to go through almost, then go to real algebra. So that's, I think, the situation. So here is another somehow interesting result, R plus in dimension 2. So this is just one of the main results obtained in a joint work with myself and Taban Far. Let's assume that R is complete local Q domain of dimension 2 with algebraically closed residue field. So this is a characteristic 0. Then there is a modular finite extension of R to S such that S is normal Gorenstein local domain. So in other words, dimension 2 R plus is a direct limit of normal Gorenstein local extension domains over R. And the proof uses some classical result by Phil Griffith on divisor class groups. And by the way, at least I don't know what happens in mixed characteristic or positive characteristic, or maybe in the case that the residue field is not algebraically closed field. So this also may be interesting question. So another recent result given by Heitmann says that, so let's take R to be complete local domain mixed characteristic. Then he proved the periodic completion of R plus is a domain. So I think no one really expected this type of result before. I don't know the reason why Heitmann decided to prove this result. But in any case, this is quite interesting. And here's a problem. Actually, this is also a research problem, which I suggested to anyone who want to do something about R plus. So is it true that the field fraction of this guy algebraically closed? Or is it true that R plus hat is absolutely integrally closed? So the reason I ask this question is because when dimension is 1, this is quite a classical result. It is known that R plus hat is an absolutely integrally closed valuation domain by Krasner's lemma. And this is quite essential result in periodic Hodge theory. But we don't know what happens in higher dimension. And I don't think Heitmann ever discusses this question in his paper. Okay, so here is also another problem which I think quite interesting. So the problem is as follows. So let's take our complete Noetherian local domain mixed characteristic. So that proved that R plus or R plus hat is a Bitcoin-Macaulay algebra. So let's pick sub R algebra T. So namely R contains T and T contains R plus, because R plus is quite huge. Maybe R plus is close to Noetherian because integral extension over R, but still T huge. So I want to really look at the intermediate extension. Then under what condition? Sorry, so I should say under what condition is T almost Macaulay? So the answer to this problem is as follows. So this is obtained in a joint work with Nakazato-san and myself. So the theorem is as follows. So take R to be complete Noetherian local domain with mixed characteristic with perfect residue field. Take system parameters starting with P, x2 through xd. Then there exists an R algebra T together with a non-zero element G such that the following hold. Namely, T contains all P power roots of P and G. And the second is the Frobenius endomorphism is surjective. The third one is the most crucial part. T is PG almost Macaulay normal domain with respect to this system parameters. Namely, I have to keep order of this sequence, because if I switch P and X2, now I don't know if this forms almost regular sequence. So it's very important to start with P. The periodic completion is integral perfectoid. And finally, this T is quite a huge extension, however, but somehow small because R is Noetherian, and this T 1 over PG. So you localize PG is a direct limit of finite et al. Are localized at PG algebras. So this makes T quite small, which is this. So let's compare this result with Bat's results. Because of the condition 5, T is much smaller than R plus. So it's impossible R plus is somehow generically et al. Over R by inverting a single element. However, so our proof relies on perfectoid methods. So more or less, the only non-trivial result is the almost parity theorem, and most part of the proof is self-contained. And I hope this is quite elementary. But in any case, if I get this result, the punchline is, again, the Hochster's partial algebra modification. T can be mapped to actual Bitcoin-Macaulay algebra. But still, I don't know what can we say about this T other than just these properties. So maybe this is also a good problem to think about. Okay, so another recent progress is a following problem. So the perfectoid geometry is quite non-Noetherian. It's far from Noetherian, but I want to go back to Noetherian world. So in any case, so is there actually a way to apply the perfectoid geometry to Noetherian rings? So this is a also big question. And I have been wondering, so what to expect. So in a just recent joint work with Ishiro-san and Nakazato-san, so we introduced a new operation called the small tilt. So I explained the tilting operation in the last talk. So this is called small tilt for a certain tower of rings using the Frobenius. So what is good about this small tilt? So this operation applies to both Noetherian and non-Noetherian rings. The small tilt is a modification of the usual tilting operation. And as a result, we showed that local log regular rings. By the way, so this is actually a generalization of normal affine semigroup rings. But it's local ring. So semigroup ring is, of course, is not local. So you can think of this as somehow completion of normal affine semigroup rings. So this class of rings behave nicely under the small tilt. So as an application, we proved a finiteness of the torsion part of the divisor class group of log regular rings under some conditions. So this proof uses equivalence of étale topology and tilting and étale homology. So here, actually, I want to emphasize that log regular rings is actually was studied by Huxter in his monumental paper of I think 1973. I forgot the title. It's just toric rings. So the paper proves normal affine semigroup rings is, of course, this normal and Cohen-Macaulay. So using his results, we can prove that log regular rings are normal and Cohen-Macaulay. And this type of rings show up in the context of logarithmic algebraic geometry. Okay, so this is our just attempt to try to apply the theory to Newtonian rings, but I think there's still much to be done. Okay, now finally, so for many people who are really interested in learning or using perfectoid geometry, without too much worry about lots of study, spending lots of time. Okay, the first problem is in view of quiz result on big Cohen-Macaulay property of R plus in positive characteristic. So he proved R plus in positive characteristic Cohen-Macaulay under the some extra assumption that this R is a homomorphic image of some Cohen-Macaulay local ring. So can we actually prove analog of this result in mixed characteristic? Now we have a result by Bargab. So Bargab's result is just any excellent local, I think excellent local domain mixed characteristic. But can we actually push this further to this situation? But for this one, I don't know. So maybe we can try without knowing too much about perfectoids or prismatic homology. And the second problem is actually there's a very interesting website by Kiran Kedolaya. Kedolaya has a website called the Non-Archimedean Scottish Book. So it's named after the, I think, Polish mathematical schooling before World War II on functional analysis, like Banach or Steinhaus. So there's a website there. He making a list many problems, not only perfectoids, but affinoid algebras, some commutative algebra questions. So he welcomes, any answer or partial answer. So this is quite interesting. You can just go to his website. I think this website directly from here. So this is his website, but I was unable to paste the URL. So just go to this website, then you can get access to this Scottish book. And the third challenge, this is quite a challenge, is just find an elementary proof of the theorem but that R plus is big Cohen-Macaulay algebra. Now this is, we really have to try, but of course I have no idea. I only offer the partial, answer, joint work with Nakazato-san on almost Cohen-Macaulay algebra, but not R plus, something which is smaller than R plus. And the fourth one, so there's one drawback on perfectoid rings. By definition, perfectoid rings are more or less, complete rings, periodically complete rings. So can one develop the whole theory of perfectoids without completion? This is also what I'm trying in joint work, but it's quite a challenging subject, but it's very attractive, very interesting. And this really means, can we actually make a theory of z-adic theory? So people just talk about p-adic theory, but I really want to see what's the z-adic theory, which means this theory takes care of all prime numbers. Okay, so but maybe this is not quite a good question. And the problem, just final problem, which I want to mention is the following one. This is called algebraic Riemann extension theorem. Riemann's extensions problem. So the statement is as follows. Let's take any ring, any commutative ring, even Noetherian ring. They pick just regular elements. I don't think I really need regularity, but let's assume this for simplicity. So let's take Fz and take n, natural numbers. So let's define a subalgebra of A localized at G. So this algebra is generated by the all elements, elements f to the n divided by G inside of this localization. The question is quite simple. So what is actually the intersection of these rings ranging over, so where actually n ranges over all in natural numbers? So actually this was studied by Andre Batt and Schulze, and they gave answers for its perfectoid. And there's also classical context studied in Barton-Belfar. So there's a paper written by him in the 70s. But other than these cases, there's also non-complete version, but we don't know so much about it. And also let's emphasize that the reason why perfectoid made success for direct summand conjecture, it's just because we can answer this question using somehow perfectoid techniques. But if you use, for example, classical algebraic geometry like scheme theory, this doesn't work. So I don't have so much time to talk about where this ring comes from. Actually, this ring comes from somehow the blow-up algebra or Riesz algebra. Okay. So I made a reference and I found just many typos. I apologize to you. But let me finally say something. How to study perfectoid spaces? So this is the biggest question. Okay, so let's finish. Let's just finish my talk. So the progress on perfectoid space is quite remarkably rapid. If you want to get learning this theory as a beginner, so you will get lost and ask a question. So where to start? So of course, there are several or possible choices depending on your final purpose. But I think what turns out to be true is just simply, I think, just try to read Peter Schulze's original paper, Perfectoid Spaces, and thank you so much.
Thank you, Kazuma, for your nice, thank you very much. We will take questions. If there are any questions, you can open your microphone and ask. Yeah, I was wondering about what is a ring which is not a homomorphic image of Cohen-Macaulay ring.
Sorry, can you say it again?
How to construct a ring, local domain, which is not homomorphic image of a Cohen-Macaulay ring.
Not homomorphic image of Cohen-Macaulay ring. I don't know actually, but there's such a ring, right?
I mean, homomorphic image of Cohen-Macaulay ring is always universally catenary, right? Yeah, we lost connection.
Okay, sorry, apologize. This time I tried to be careful, but somehow again this connection, so I don't know.
Yeah. So
okay, so the question is actually non-universal, non-catenary. I think non-catenary local domain, right? Non-catenary.
Yeah. So rings which are homomorphic image of Cohen-Macaulay ring are catenary. They are
catenary, universal catenary, right?
Yeah.
Yes, so, I think there are such examples.
I think there is I think long ago there was a ring constructed by Renault, Michael Renault, so that it is not formally unmixed. Yeah.
Okay. Yes.
Yeah, but those are a bit difficult to write. Those rings.
Yes. Yeah. For example, if you specify dimension 3, dimension 4, can we find such example? I think there are lots of papers. Yes.
Yeah. But one doesn't have a counterexample to existence of big Cohen-Macaulay algebra without the assumption of the ring being homomorphic image of Cohen-Macaulay. You said that
Mhm,
uh, Key's result is the best result for existence of big Cohen-Macaulay algebra.
mhm.
Okay.
So, okay, so anyway, Bitcoin Macaulay algebra can be constructed over any Netherian encoding. But when you actually take R plus, so there's I think counterexample. So for example, Ray Heitman constructed, I think even positive characteristic dimension for local UFE and then maybe some plus some other technical condition. So he proved that he constructed example R such that R plus is not going Macaulay.
Okay. Okay.
Mhm. So of course, this is not. I guess yeah, maybe even universal catenary plus something. I think he gave example in Journal of Algebra.
Ah.
Mhm,
So the problem lies in making sure that every system of parameters
mhm,
is a regular sequence.
mhm, mhm, mhm.
Okay. Okay. That
Yeah.
after
So
you used to call them balanced Cohen-Macaulay
yes,
algebra.
yes. So this so Bargov's result says, of course, if you take R plus dimension, I think 4, so then this is not balanced Cohen Macaulay. So this is the Cohen Macaulay. If you order by P, then any system of parameters is a regular sequence. So it's a Cohen Macaulay algebra, but not balanced.
Okay.
Mhm.
Thank you. Thank you very
Thank
much.
you.
Are there any other questions? It's a new challenging field, and as Kazuma said, that if you want to read more, you can
Mhm,
request him for his lecture notes.
mhm,
We will be happy to send.
mhm.
Yeah.
Yes, yes. So I anyway, I just correct my slides and send you.
Thank you.
Thank you.